It's on.
It's on. Hello, ladies and gentlemen, and welcome to another episode of the New York City Category Theory Seminar. Today we're having Elias Cooper. It's our second time he's speaking. He's talking about algebraic string diagrams and manifest covariance theorems. There's actually two things going on here. You should be able to see Elias's slides, and you should be able to see Elias. So if that's okay with you in the cloud world, it's just, if it's not okay, let us know. Take it away, Elias.
The reason there's a hyphen over here is because I don't want to get confused with string diagrams in Moataz category theory, and I'll explain more about that. The reason there's a hyphen here is because manifest covariance usually does not have that, and if you talked about the covariant derivatives in general relativity theory, that's not a derivative, it's a qualified kind of calculation. So I had to stick that in and make sure. Now, I'm going to go down this list of theorems very quickly. I'm going to show each one very quickly. Just in case I run out of time, I want to make sure at least you've seen what I'm aiming at. And then I'm going to go back and go through. Now, there are 68 slides, and maybe I can fit that in, we'll see. But certainly, I know you'll interrupt me whenever you want. Thank you. All right, so just to go through these theorems, this screen is a little small, but here's a theorem. These are the algebraic string diagrams I'm talking about. They look like that. That's not a new invention, but it's very convenient for me to organize things in a specific way that I'm going to show you.
So when basically right there, they go back to showing still left. So there's when you're invented linear algebra, there was long diagram.
Well, I don't go back that far. I go back to Penrose.
Yeah.
Yeah. Did he get it from them?
They had it. That's what they called hyper somethings. They used to, they were doing invariant theory. They had to do a lot of contractive tensors.
Yes,
so they
yes.
Sooner or later came out with the idea of
I didn't know
drawing them
that.
as such diagrams.
So there's a deep history.
It goes back as
Yeah.
far as multilinear algebra.
Speaking of which, basic theorem, the isomorphism between multilinear maps, scalar valued multilinear maps, are times contravariant as times covariant, corresponding to tensors, which I've always wanted to understand, but this does help. Yeah,
Elias, I'm just going to press pause for a second.
the crystal symbols have this nice formula, and I'll be coming back to proving that formula. I'm calling this the Wilmore-Palatini theorem, and I'll talk about that some more, but this is how covariant derivative is extended from vector fields to tensor fields in general. And it's a beautiful thing, and that's more. By the way, this is how it is presented and explained in the phone book, the gravitation book by Meister, Thorne, and Wheeler, and this is my way of writing it with a little bit of my string diagram notation for contractions. Covariant derivative theorem is that an affine connection commutes with changes of coordinates. That's really what covariance is about and what the talk is about.
Wait, can I just slow you down for a second?
Please.
So what's the setting? We have a manifold.
I'm going to give that in the talk.
Later, okay.
This is just make sure I've covered everything
Okay.
in case we run out of time, and at least I've shown you what the whole picture is. Parallelism is an essential concept in Riemannian geometry, and I have a little bit to say about that. Lie brackets are an important component in the kinds of calculations, as will be seen. And the Riemannian geometry theorem, I'm giving a sort of a baby version of it in the talk, and we'll come back to that. And then, of course, the manifest covariance theorem is right here. And now I'll go through the topic. Okay. This is the abstract for the talk. I put in bold the only thing worth reading to, other than setting it up about the importance of covariance in physics, especially relativistic physics. The point is that it's a syntactic concept. And the word manifest means that you can look at a formula and tell that it's covariant if you know the syntax. And I'm going to explain that. Related work. I have not read in detail this, but it's a famous work about tensor networks, which are all about contraction. And so are my string diagrams. More to the gathering here of category theorists is the Joyal and Street paper. Again, I haven't read this whole paper, but I know that monoidal category theory string diagrams go back to this. And here's Penrose's version of string diagrams. And again, this is algebraic string diagrams in my sense, not in the sense of monoidal category theory, which I'm hoping to make that distinction extremely clear shortly. But I will just point out that the uppercase Greek letters here correspond to the triangle and the circle.
So for you, tensor product means tensor product of vector spaces, not tensor product in a monoidal category.
Correct, but the category of finite dimensional
Sure.
vector spaces is
Yeah.
a
Right, but you're
monoidal-
working in that category, not in some arbitrary category.
Correct. I will just say one other thing about this. I don't care for having more than one notation for the same thing. So I don't use circles and triangles. I use the letters. Keep it simple. Florian taught me the concept of cognitive load. It's very hard to things if there's too much to deal with. So I try to minimize. So here's the kind of observation that I hope is worthwhile, but you'll tell me whether I'm making a mistake. But I believe there are two category errors in this context. One, philosophically speaking, the string diagrams in monoidal category theory are not about contraction. They're about the flow of process. The strings are actually objects in a category, right? And the nodes are functions or morphisms of some kind that process the data in the objects. So it's important, I think, to make a distinction between contraction indices connected by lines and processes in the monoidal string category. But there's also a category theoric error. Contractions is a bilinear, let's face it, dot product is the first high school level contraction that we see. You know, sum of products, which is a function in Excel. Sum product is a function in Excel. So Penrose diagrams, I say here, and I'm not going to read this all out, but that's the distinction I'm making and the confusion in the literature.
Is it contraction, not a composition with two morphisms?
Well, you can rewrite it that way, but I personally think of it as a sum of products. And if you want to break that down into a diagram with a composition,
Vector times a column.
sure. But in tensors, when you contract tensors, you're taking one coordinate from the contravariant side, one coordinate from the covariant side, and I'll talk some more about that. And if you want to bring up the connection with the computation you said, I'll certainly will probably show pictures of what you said somewhere along the line, but we'll see. Okay, so now historical matter, personal story. I'm going to try to keep this short, but I really have to say it because I have motivation to explain that I got interested in relativity theory when I was about 13 years old, reading books, comic books, Superman, he could fly, right? And also Peter Pan could fly, and I wanted to fly. So I wanted to invent anti-gravity. And I said, well, does anybody know about that? And so I learned about Albert Einstein, and got, general relativity theory. And I was friends with a bunch of fellows in Brooklyn, East 15th Street. Bobby Riesenberg was one of my buddies, and he became a professional physicist. He actually did work in gravitational theory. So that was I was 13 years old. That's what that's about. But then later on, I became acquainted with Ralph Abraham, and so I would just want to stick in a little piece here in memoriam, because he was a good friend, a man who encouraged me, and in particular, I took a course with him, and it's the only good grade I ever got in mathematics. I got an A+ from Ralph. He taught a course in differential geometry and relativity theory, which is what this talk is about ultimately. And that was in 1963, Columbia University School of Engineering. And then 5 years later, we had maintained contact and friendship. And
So there's standard core courses.
oh yeah, and this is a very well-known book, Foundations of Mechanics by Abraham and Marsden. And this piece here is right up there. So there's want to acknowledge that the eagle represents a hodgepodge group of Princeton graduate students, and plus myself from Columbia, together with someone you know, Kenneth McAloon.
Who just passed away.
I didn't know that.
Yeah.
Well, then I'm going to put this in memoriam to him and him. This was some years later in the 1980s. I was already working somewhere else, and but we would get together because Ken and Ralph had created a group of mathematicians and students to write a series of textbooks, which were published. And I was in that group, and we had some great old times together in California. And Ken and Ralph introduced me to Lauvier in a bar off some side street in Paris in about 1970. And that's how I got to be in Lauvier's group for a while in the early 1970s.
Yeah.
So
You have digressed.
I have what?
Digressed,
Have I?
yes.
Well, there's Ralph, and that's the end of the digression. Now, various books have mentioned covariance in various ways, and I've always been confused about it. Talking about equations keeping their same form, one of the basic notions in physics. Well, I don't know what that really means, and today I will tell you what it really means. But even educators have worried about trying to explain what it is, and this is an article on that. And one of the better explanations I ever saw started with the definition of the word invariant. You mentioned Sylvester earlier. So an invariant is the same in all coordinate systems, so you don't have to worry about covariance. And then another example in another book, Space-Time and Geometry. This is all they say, well, the author, I should say, says about explaining covariance. It has to do with a matter of jargon. That doesn't explain anything to me. Oh, well, it says one little thing that's important. It says, if it's written in terms of tensors, it's covariant. And that is, I'm sorry, more to be, hello.
One share.
I got that. Mice are very hardy.
You don't need that?
And
Sorry, but anyway.
so here is again in that book by Jakob Schwitgenberg, in his book Physics from Symmetry. He gives the first decent explanation from which I am deriving the rest of what I have to say, because he gives actual equations to look at. He says this formula in one coordinate system involving coefficients little a, little b, and little c, calculated with some input values, upper a, b, and c, give this value e. And then if you change coordinate system, you still use the same A, B, and C and the same summation for the form of the calculation. So it's an idea of getting hands on what is meant by the word form. Okay. So you see here, the A is not the same A as that. There's no B here. And so it's not covariant, not the same form. So now I'm going into the technology that I'm going to use for my proofs of the theorems that I showed earlier. First of all, I'm going to introduce a category of domain. Yes.
There was a question on the.
Hold on.
Here?
It was like, so form, so.
The form is a polynomial decomposition?
No. Form is what's invariant under a diffeomorphism. That's the real point. It's more general.
Or if it transforms like a form.
So a domain, a category of domains is just something that derives from trying to, again, reduce my cognitive load. Usually in talking about general relativity, we have like a manifold, an atlas of charts, and possibly a maximal atlas, because you just throw in every chart that matches any that are already in the atlas, and you have a maximal atlas. It's a rather complicated thing, and I felt or feel that the heart of the matter is when two charts overlap. When two charts overlap, that's when you have a diffeomorphism between the coordinates from one of the charts to the coordinates in the other chart. So it's the overlaps that matter. So the category of domains is really the overlaps. And it's a very simple category. The objects in the category are open sets in Rn and varying from 1 up. And morphisms are C infinity maps. Smooth, I'll just call them smooth maps. Okay. This is just telling you about some of the notation that I have found extremely convenient, especially down here, where X bar is an m-dimensional variable based on n variables, the X1s. There should not be a bar over there. I just saw that. Okay, no bar there. It's correct here. And that notation is very convenient because it reduces the cognitive load by not needing to use a name for the function. I'm using the output variable, the dependent variable, as the name of the function. So there's an opportunity for confusion there, because if you say, for example, X bar equals X, X bar equals X bar of X, then you can substitute X bar for X bar and you get an infinite thing.
So this
That's
is why you use
ridiculous.
a double equal sign. to point out-
No, okay, thank you for reminding me. That just means the left side is an abbreviation for the right side. Okay. Officially, there should be like an F here.
Right, but that's what I'm saying. So you see that, that tells you I can't do like an or an equal sign and do the substitution I mentioned.
Thank you.
So how is this related to manifolds?
I will come back to that, although if
That category.
this category is sort of the category of the overlaps of coordinate charts.
Yeah.
It's the category of the diffeomorphisms arising from the composition of the inverse of one chart's coordinate map with the forward map of the other chart.
I thought you could build all manifolds from this category.
Yes, and that's a theorem.
Yeah. So.
Yes, and
Like,
ChatGPT proved that theorem for me. But I by the way, my nickname for ChatGPT is Jippity with a small g, because it's sort of like having a powerful assistant who's kind of dumb. And I did not include
the perfect kind of assistant.
I did not include that, although I have
All
it in
graduate
a-
students.
I have
He said
it
all
in a
graduate.
separate document, and it involves, interestingly enough, sheaf theory,
Yeah.
using open covers.
So manifold splitting.
It is John.
So,
Still
okay,
weird
now
stuff.
special examples of the domain, category of domains. You can have a curve on an open interval, that's from R1. And you can have a scalar field over a domain. And if you have a curve in the domain and a scalar field over the domain, then you have the values of the scalar field varying across the curve. And so you get into, directional derivatives. And that's all by the by. It just comes for free as long as you have partial derivatives, which is, by the way, the only kind of derivative in the story is partial derivative. In the literature, there are big D's, little d's, deltas, all kinds of symbols used for derivatives, but there's really, in my use here, only one kind of derivative, partial derivative, and everything else is built from that.
Of course.
Okay, so, and then, there's an adjunction possible here. It's a little currying. If you have a n-valued dependent variable defined on a domain, you can bring the n over to the other side of the adjunction, and so you can have a map from the list of digits from 1 to n into the smooth maps from U to the real number, to the scalars. And then here's a notation I use over and over again. If capital X is your field, evaluated at a point P, its ith coordinate is denoted by that. And so you have the category of finite dimensional vector spaces. Just to be very clear, Abelian group together with scalar multiplication and the usual calculations you can do with that. And you might have a basis B1 or Bn. And my real point in this slide, of course, is to show you my first algebraic string diagram, which is this contraction down here. That gets, okay, so you got 1, 2, 3 letters here and only 2 letters here. I saved a letter with a line. You're familiar with this basic adjunction? Here's a little kind of a proof. The idea that given any finite set, you can take all the linear combinations over some scalar field, complex numbers, real numbers. I'm doing real numbers exclusively.
The forgetful functor is not really there because
Pardon me?
the forgetful functor is not really there because take a finite dimensional vector space. It doesn't, it's not a finite set. It's an infinite set.
Oh, look at that. Mistake.
Yeah.
What should it be?
Set. But it doesn't, it works for,
Sets here?
it works for,
Dimension.
And then all vector spaces on.
Right, unless you have a finite field, you're gonna get an infinite set.
Thanks for that. Okay, so I'll put set here
okay, but
and then I'm good.
no,
Still
then,
okay, because you just do a big.
Then I gotta get rid of the FD.
right.
Right, okay, so now you fixed it. Thank you. Okay,
I think it's still okay, it's dimension. Forgetful functor is the dimension.
So you get an adjunction,
It's a set.
but
It's a Vasily set.
It's a finite set.
The dimension?
It's
do
a-
you,
you have a
you-
finite
it's a,
dimension
well, it's a cardinal.
of a finite dimensional vector space. Yeah, the dimension is a set, yes.
All right, so.
N is a set.
But would free be the left adjoint?
yeah, it's, does the adjunction stay?
Gotta work this out.
N is a set.
Okay, so,
I believe, I agree, I just don't think it's gonna be an adjoint.
Oh,
yeah, I'm gonna have to remove that slide.
It's okay, it's okay,
But everything else will go through with a.
basis then.
How's that a
the
function?
basis really doesn't work, it's not natural, nothing's really
Alright.
assumed.
Well, but
It's a
before we
great.
move on, what was the point? Maybe what was the point?
Well, I'm gonna save that.
Just context.
Just,
I'm not gonna use it per se, I'm not gonna use my non-forgetful functor for anything.
That's true.
I am gonna use free functor. Basic theorem that for finite dimensional vector spaces, such a vector space is isomorphic to its double dual. And that is very important in connection with contravariance and covariance, as will be developed later. But I had to make sure that that's a solid thing because I will refer to it later. So I gave a short proof of that.
That's McLean and Eilenberg's motivation. That map.
Is that
It's the first page of the 1945 page.
I mean, right.
Right, the whole point was they're asking,
That's-
what does it mean for it to be natural, so they have to invent category theory? To answer
I
that
mean,
question.
I've studied that paper, but I didn't realize it stuck somewhere in the back of me to become a
Yes.
slide.
Makes sense in finite
All
dimension.
right, so here's a proof. By the way, some of the proofs I've read of this depend on, once you get to the point where that it's an injection, then they say, well, we're talking about injecting a finite dimensional space V into a finite dimensional space V double star. And since it's injective, and the dimension of V double star is also the same dimension, then they must be isomorphic. I'm not doing that. I'm just giving the inverse function right up. Now, talking about monoidal categories, because I know who's here, I just want to say that finite dimensional vector spaces is a symmetric closed monoidal rigid category. Rigid referring to the star, the duality. And so I just wanted to spell these out a little bit for the purpose of drawing the next picture, which is this. This is really the zigzag theorem in monoidal category version of string diagrams. It's the only time I'm going to really talk about monoidal string diagrams, because like I said, I want to distinguish those from Penrose string diagrams. And the thing I had to realize is that the associator, this guy here, that's the inflection point in a zigzag. Everybody knows that, right? Well, I thought I had found something worth saying, so I said it. Okay, so now we get to calculus. We need tangent vectors. There are lots of ways to construct a tangent bundle of a manifold. The way Abraham taught it was by equivalence classes of differentiable curves. If two curves are tangent or at a point, then that defines representatives of an equivalence class, and then the whole equivalence class is the vector. That's too big for me, but I really liked it when I found that there's an alternative in terms of derivations, which is an pure algebraic concept. It's linear and Leibnizian. I don't know if other people use the word Leibnizian, but I prefer to say that than say it obeys the Leibniz rule, UDV plus VD. So this is also the only place where it looks like something a little more substantial, because sheaves of germs of holomorphic functions are defined in terms of neighborhoods of a point where two functions agree, but not necessarily over the rest of the manifold. So this is the only place where those are mentioned, because they immediately give us the coordinate derivative functions and the dimensionality of the tangent space. Okay. I show this primarily for the notation because I know you all know calculus, but I just want to point out that in a way, the whole thing is trivial, because everything is in a single domain in a space in Rn. So really, you're just talking about partial derivatives in Rn. Yeah.
Just a question
Yeah.
on the notation.
Yeah.
The circle with the C in it that
Yeah.
looks like copyright.
Yeah. I made that up.
Oh, that's you. That's yours.
Yeah, it's supposed to suggest to you a small neighborhood inside of a domain. That's the
Okay,
mnemonic. Does that work?
that's perfect.
Should we be concerned that that notation means C infinity before you define derivatives? And previous slide, right?
Let me see what you asked.
Where you're telling us what C is, and it's the set of C infinity functions, but should we know what C
It's not
infinity
all, it's not all C infinity functions, locally C infinity.
Well, no, of course, yeah, that presumes you know. So the point is, the idea is, given C infinity, I think of it as an algebra.
Mhm.
Then I find in that algebra, I get the derivations, which have to correspond to the ordinary derivatives I use.
Okay, got it.
Yeah, but so the point is that, yeah, we need it to define, but once we define it, we can algebraically recover the notions we need just from the algebra of C infinity. So, notation for a domain U at a point P in the domain, we have the set P10, this is a Roman T. I need more than T, so, but this is the basic one. This is just a set of those tangential derivations, the linear Leibnizian functions on copyright. And this theorem here shows that this thing here is a vector space of dimension n. And the interesting thing to me is that the proof I saw of this in this book here, Tensor Analysis on Manifolds by Bishop and Goldberg, that they take a page and a half. It's basically an AP course in calculus, a high school AP course in calculus. To prove this theorem, they need the fundamental theorem of calculus, Taylor's theorem, a bunch of algebra. It's an important theorem because it sets the stage for everything else, but just giving you that the partial derivatives with respect to the coordinates are a basis. Why did I put a link here? Oh, I just wanted to point out that the concept of linear and Leibnizian occurs over and over again in this subject. It's not just to define tangent space. It comes up elsewhere. Okay, I'm not spelling out any kind of proofs here. I think it's kind of straightforward that given U, a domain in the sense that I'm talking about as an open subset of Rn, you get not only the tangent vector space at each point, but you get the cotangent vector space at each point, which is just the dual of the tangent vector space, the star. And then if you bunch them all together disjointly over the whole domain, as in this union here with a dot, you get the bundle space of the bundle, the total space of the bundle, and likewise for the dual. And so I remind us of the terminology, but also the most important concept when you have a bundle is a section of the bundle, which assigns to each point in the base space, U in this case, vector at each point above that, each of those points down there. And I just want to say again why, in a sense, this whole thing is kind of trivial, because I am not using manifolds, I'm just using a domain. The union, the total space is really just canonically isomorphic to a coproduct of copies of Rn. Because each one of these is an Rn, or I should say, an isomorphic to an Rn, and combine them with this union here turns into that coproduct there. And dually for the cotangent bundle. We okay?
Just
It's really kind of like this. The open subset of Rn is not canonically as.
No, these are not open sets of Rn. These are tangent spaces defined on the whole open set.
Oh.
Okay, and again, as I said, linear and Leibnizian things come up over and over again, and you have the coordinate functions. I don't know how to pronounce that. Partial derivative function defines on the scalar fields
0, 0. That's a new notation. So far I have 1, 0, 0, 0. I didn't say it enough. 0, 0 just means scalar field, smooth scalar field on a domain. Okay. And vector fields like X define an operation on scalar fields, namely directional derivative. So that's what this is about, and this is the notation that I use for it. And again, you could say to me, why didn't you put a line here to get rid of this contraction? And the answer is, I forgot. But that really should be written as an X with a, as previously demonstrated, a line, always from an upper index to a lower index, okay? And taking all available partial derivatives, putting them together into a matrix, the Jacobian matrix, gives you a morphism in the category of tangent spaces over domains. And this is a very familiar standard stuff, I know, but I just wanted to make sure that notation and the concept was available for further discussion. There is in the literature this thing that instead of using the Jacobian or a T for the functor defined by a smooth map between domains, they use a star on the function phi. So phi, I don't know where it says phi, yeah. Here's phi. It goes from a domain U to a domain U bar. And you take its Jacobian, there it is. There's a tangent vector. There's the output you were saying, somebody said column vector, that's the column vector for a tangent vector. And this is the official algebraic definition of doing that. Yeah, that's a J down there. And this is the algebraic string diagram equivalent of what I just said. That was the point, is that if you have a tangent vector in domain U and apply a smooth function phi to, let's say, U bar, then the contraction is shown by this line here. And I put an I there only for convenience. There's no need for it because there's only one index on a vector. And there's only one lower index on a matrix and only one upper index on a matrix. So these are not really necessary. So this means I abbreviate that to this. And then the result of that contraction has one loose index, and there it is on the image of X by phi, giving X bar. And then now this down here is an afterthought. I don't know whether it's kosher, but the thing is the whole talk is based on derivatives. Everything is derivatives. The Jacobian is all derivatives. So I said to myself, well, gee, is there anything in this talk that's like an integral? Yeah, a contraction is a sum of products, and so is an integral. Infinite, though it may be, but you can even use hyper integers to define what looks exactly the same as a contraction for the definition of an integral for continuous functions in the hyperreal universe. Mm-hmm. Okay? So I figured I might as well throw that in just to say that I'm doing calculus. Now this is in Abraham Marsden's book, 1.7.5. This is the basic formula for transformation of coordinates using indices. And you can see there's a lot of notation here from the textbook. And I boil it down to this picture down here. So applying coordinate transformation to a tensor, lower t, which has these indices in the contravariant place and these indices in the covariant place. Well, t bar comes from key by the string diagram. I call it an algebraic string diagram. And up here, where Abraham and Mogden say that B times A equals A times B equals the Dirac delta, well, that's what this string diagram equation, these two equations say. So again, I'm about reducing cognitive load. I just want to say, before I show more string diagrams, I just want to say a little bit more. One must keep in the back of one's mind that these upper lines here are ordered from left to right, just as they are here. This goes from T1, I1 to I, oh, that should be IN there, and J1 to JS. That's an ordering. And so you can't just arbitrarily rearrange these algebraic string diagrams. You have to keep in mind some ordering. Yes, sir.
So you said that in the second A1 at the top index in your formula.
Yeah.
In the formula
This formula,
should go from 1 to
R. Actually, this should go from 1 to R, and this should go from 1 to S. Wow. I don't know.
okay.
Yeah.
And then to the left of that, it says on the top one, it says 1 to F. Should that be R also?
Yes, absolutely.
Okay.
Oh, yeah. You don't know how many times I've gone over these.
Yeah, no, you believe me. Yeah, I know you start to hallucinate when you do this.
So
It's almost a way to advocate for the pictures.
Yes. Yeah.
thank you for that. You told me your name earlier. I think
John.
John. Thank you, John. I want to say a tad more about that. This kind of notation here is a linear notation, no question about it. These things can be moved around. These blobs can be moved around as long as you keep the connections and the ordering of the connections. So that's Penrose's diagram was like that. He just moved them around. Now I'm going to say another word about that. In monoidal string diagrams, you're not free to just move things around. At every paper I've seen about monoidal string diagrams, they make sure that you are told ahead of time what direction you're reading the diagram. Are you reading it from bottom up or left to right or top to down? And all of those occur. To me, that's excessive information. You shouldn't have to do that. Then again, I'm saying you do have to keep track of this. So, but I think these diagrams are very flexible as long as you keep ordering in mind. Okay, so multilinear scalar valued functions are isomorphic to tensor products. But you got to be a little careful here. You see that you've got stars up here and no stars here, and yet you got the same R. And the reason why? V equals V star star. And I always remind myself why that is by saying, well, what if you just have R equals 1 and S equals 0? Well, then you've got E star, a linear map from E star to R. Well, that's an element of E star star. Right? Linear maps on linear maps is the original thing. So that's that. And here's a proof that I wrote for just amusement, because that calculation is straightforward, just shifting things from right to left, basically, and that's what these strings are doing. So at the top, you have a tensor evaluated on k tangent vectors, x1 to xk, well, each of those has an expansion in terms of the base point. I'm not showing the point, but this is all at a 1 point. And so these are the contractions that define the expansions of the tangent vectors. And then you move those to the left one at a time because of linearity. And you end up moving them all out. All of the coefficients x are being moved out, and you're just left with the tensor. So multilinear function to tensor. Okay, now we get to the real good stuff in terms of derivatives on a manifold. An affine connection is a multilinear map, but it has a property. And I want to insist on just how that works. A tangent vector over, a tangent vector, I'm using a script T here because now I'm talking about smooth sections. That's where I just switched from a Roman T to a curly T because of smoothness. So a connection takes a pair of tangent vectors and gives you another tangent vector. But it's under a certain condition, namely that it's R-linear in both coordinates, but Leibnizian in the second coordinate. That's a beautiful thing. Beautiful thing. It makes, I don't know, and perhaps you can tell me, whether there is in the literature of the concept of a multilinear map together with a property. That means it's a structure. Eilenberg taught me that a structure is data and conditions. Well, that's the data. These are conditions. So a connection is a structure, and we will see how that goes. But now we get to the thing that confused me infinitely when I was 13 years old, because I saw a book that had these equations with lots of partial derivatives, and it kept talking about Christoffel symbols not being tensors. And what is a Christoffel symbol? I couldn't understand it. Well, here's what it is. You take two vectors, like two basis vectors, di and dj, two basis vectors, because it is R-linear, so that's enough. But that is a vector, so it has to expand in terms of vectors. And that's why you have three coordinates on a Christoffel symbol. You have the coordinates for the inputs and the coordinate for the expansion of the output. And then there's a theorem. Take two arbitrary smooth vector fields x and y and expand them. Use linearity to pull out the coefficient on the left input. But then you see you have to deal with the covariant, the nabla of the right-hand side. So expand that out and go through this, and you end up with this algebraic string diagram. That is to say, the covariant derivative of y with respect to x, use it, the kth component of it. I put the k here. Okay, there. Put the k here. The kth component is obtained by this little picture here, which to me, if I take the y with its string and shove it over to the right, the Christoffel symbol is like a binary operator. And I thought that was interesting.
So intuitively, what's a connection?
Okay, I'm going to get ahead of myself. A connection gives you the connection between the different tangent spaces at different points. That's what it is. It's the connection between the tangent spaces by parallel transport along a geodesic. And the connection gives you the tools to do that.
Well, one way you can think is you take your three indices on the Christoffel. So one of them will tell you the direction, tells you which direction I'm transporting in. The other tells you what vector I'm transporting, and it gives me the result of that.
Yeah, but with components that are determined by the structure.
Sure.
The K. Are we good?
Makes more sense.
Okay, so given a diffeomorphism between two domains, we're interested in how the Christoffel symbols change when you change the coordinates. And this is the standard formula. Gamma bar is determined in terms of gamma by, forget about the second term just for a moment. It's determined the usual transformation for tensors with the partial derivatives of the coordinate change down here. But then there's this new thing here. second derivative. Now, back in the days when I was taking this course with Ralph, we were made aware of Serge Lang's tiny little book on differential manifolds. Beautiful, beautiful category theory, explaining differential theory. And I didn't at all understand what he was talking about, but he said there was a thing called a spray that lived in the second tangent bundle. And that's what that is. That's in the second tangent bundle. It's the second derivative. Derivative of the derivative. So I still don't know what a spray is, but I know this is the first example. And now you want to prove fundamental theorem. You want to prove that the covariant derivative is covariant. That's why I had to put the hyphen in the title of the talk. And so we have to do a calculation. So what we're trying to prove is that a diagram is commutative. You have the Jacobian on the left edge, the Jacobian on the right. This is Jacobian on two variables on the left end for the input of a connection. And you want to show the diagram is commutative so that you're required to show that the structure of the connection is preserved, that the second coordinate is also Leibnizian. Linearity is not hard, it's all Jacobians. But showing that the second coordinate, when you do, well, I drew this upward, but with a J bar, but the way I'm proving it is to go up, over, and down. But you could have started up here and go down and over and down, but then just writing it in a different way. So here's the calculation. There's an intermediate part of the calculation. Here's the end of the calculation. And the nice thing that happens is that there's a cancellation, which leads to the second order derivative. And then we show what it looks like in an algebraic string diagram, which to me is helpful because it shows that if you left out the spray part or the second derivative part, you have a tensor transformation on the upper index and on the two lower indices by the Jacobian. Without that, gamma would be a tensor, but it ain't. Then there's a generalization of the covariant derivative, covariance, which says that you can define the covariant derivative of any tensor. I and J here are strings of indices. Capital I is I1 to IR. Capital J is J1 to JS. And this formula is written in partially written in my string diagram notation. And I want to explain what it means. What it means is this. You're going to take the partial derivative of index L of the tensor, fine, and then add to it and subtract from it terms that correspond to the connection. So let's take corresponding to the upper indices. You take I1 through IR up here, you drop IP out, and you do this for each one of them. You drop IP out, replace it by a contraction with a covariant index, so to speak, of the Christoffel symbol, and add those all together. That takes care of transforming the Christoffel notation for the upper index. For the lower index, you subtract, but it's the same idea. You drop out JQ and add in a contraction with the upper index of gamma. Now, Abraham and Marsden give a reference to this on page 148, but perhaps you're familiar with the absolute differential calculus, one of the most challenging books by Levi Civita. I think I'm pronouncing it right. It's Levi Civita. Anyhow, they wrote an old book on the absolute differential calculus, and in which they actually show an equivalent to this formula and attributed to A. Palatini in 1919. So this is old standard stuff. Now, in the fat book by Meister, Thorne, and Rieler, they're trying to explain that formula by giving an example. They have a once contravariant, twice covariant S alpha beta gamma tensor, and the semicolon means covariant derivative with respect to the delta coordinate, and they give this formula for it. And you see here's the plus sign that I have here. Here's the minus signs here because you have two covariant indices, so you get two terms downstairs and one term upstairs. And then they try to explain the algorithm for calculating this with these annotations. And that's as most you can learn from that book. But here's that theorem I mentioned earlier, proving that it's covariant. And here's a conceptual proof, no indices. And what you see is the nabla bar here sneaks its way through the Jacobians and due to linearity and taking account of the Leibnizian, it ends up over here, and then you're home free. New subject going back to parallelism. We need to deal with the idea of taking a derivative along a curve. And so I never understood what they meant by that until I drew this picture, this diagram, this commutative diagram, and I want to say some words about this. Here's nabla, the affine connection, two inputs, one output. You can project on the first, you can project on the second. By the way, for projections, I'm just using a binary string to say which coordinate I'm projecting to. So 1, 0 means the first coordinate, 0, 1 means the second coordinate. Okay. Now, so you have the Jacobian on the top of this curve, and you have a vector field down here. So we're interested in the derivative of the vector field along the curve. So, well, the product now, right? So I have the dotted arrow by category theory, and I can compose that with nabla and get a map from the vectors and the points, I should say the tangent vectors of the curve to the tangent vectors of the curve and the tangent vectors. And the reason why this is significant as I go forward is that this whole diagram is dependent upon combining things only by composition and tupling. Okay? And that's the key to manifest covariance. So I'll be explaining that, but that's why this diagram is important to me. The other reason this diagram is important to me is because it sets the stage for doing something that I have not done, but this diagram is parameterized by U. Right? So you could construct a functor which, given a domain U, provides you the covariant derivative of a vector field along a curve. So I'll be talking more about that. Going back to parallelism, here's a short sequence of theorems based on Abraham Martin's book. First of all, the vector field is parallel to itself along the curve if its covariant derivative is 0. And the curve is a geodesic if the derivative of the curve is autoparallel. And J gamma is the derivative of the curve. Okay? And this is the fundamental theorem of parallel translation, which uses this notation to define what I mentioned earlier, sir. The connection, nabla, is what connects the tangent vectors at one point on the curve, point S, to the tangent vectors at another point on the curve, T. There's some brackets around that. Anyhow, this tau is parallel transport. It's functorial in the points along the curve. In other words, from S to T moves a vector from there to there, and then from T to whatever, and is another movement, and the total movement is equal to the composition of the two movements. And parallel transport is, I don't know, I think it's one of the most interesting things about a manifold is that you can do that as long as you have a connection that connects the fields at different points, a vector field. Questions? So, and I summarized that down at the bottom here.
And this says nothing about existence.
The existence follows from solving an ordinary differential equation. That's so beautiful. I think that's just wonderful. You have two parameters, a point and a vector at a point, and you want to move that vector to another point parallel to itself. And they always show as an example in the textbooks a sphere with a vector orthogonal to the equator, and then they move it up to the North Pole, and that gets you a vector in one direction. Then they move it along the equator and bring it up. Oh, it's different. Okay, new topic. The Lie bracket of two smooth vector fields is, again, sort of like a connection. It's not a connection, but it has the same pair of inputs and a smooth vector field as an output, but it's given by this formula here, which is a commutator. It's x of y minus y of x. And the theorem is that the Lie bracket is actually covariant. Einstein uses that. We'll get to that. Okay, so you have to prove it. So we start a calculation, break everything down into components, keep on going, and then an interesting thing happens. And in the book where I saw this beginning of this proof, Sean Carroll's book, Sean Carroll says it is an interesting exercise to show that due to certain cancellations that the Lie bracket really is covariant, but they don't show the proof. Here's the proof. This piece here, second derivative here, is actually going to cancel this one. And so you're left with the cancellation resulting in L bar of X bar Y bar is equal to bar of L X Y. That's a commutative diagrams. I didn't draw it.
Another way of thinking about it is
Yes,
that, your Lie bracket is saying, well, if I think of these as vector fields as derivations, I'm taking their commutator and I just check that the commutator derivation is checking commutator derivation state
Exactly, right.
derivation.
Yeah, that's the commutative diagram. And then I'll redraw that with strings. Now, personally, I think that's kind of ugly. But I also said to myself, and I actually worked with Jippity for a little bit on this, to write a LaTeX style file to construct neatly these contractions. And maybe if it was drawn neatly, it would be a little more appealing. But I'll tell you this, you never want to do. In fact, I got so tired of it, I left a couple of them out down here because I couldn't sneak in the contractions at the bottom. This one.
It's not planar.
Okay.
You have to cross lines.
Okay, so then here's this little thing. I've had it in my mind for a very long time that notation, if it's done right, carefully, it has a pattern to it in itself. And it's a visual pattern. So I used to call that the geometry of notation. But in this case, the geometry of notation is the geometry of notation for differential geometry, for what it's worth. Okay, new topic. Trying to see what the real underlying mechanisms are from a category theoretic viewpoint. So remember that the domain DOM is a category of open sets in Rn, but within that category are the diffeomorphisms between open sets from Rn to Rn. So we'll call that diff, and these inclusions follow the definition. Now, the point is that I can start to define what's a geometric object. It's a functor from the groupoid of diffeomorphisms to the category of finite dimensional vector spaces. It assigns a vector space to each domain, and using the Jacobian of the diffeomorphism now, you get. So bottom line, a geometric object in general is a representation of the diffeomorphism groupoid. What's the advantage of that? I have not mentioned coordinates at all in defining a geometric object.
One question, because you
Yeah.
could assign the vector space to the whole domain, but I thought, wouldn't you say it each, usually the fibers, so you have a vector space for each point in the domain, not just for the one vector space for the whole domain.
We should write it as a bundle now.
Yes,
Yes.
so, right, to just, instead of vector space, a domain vector space to each point in the domain.
Yes, sir.
Yeah, but the point is, like, you're not assigning a finite dimensional vector space to
The whole domain.
all of them.
No.
Yeah.
Do you mean what you say or no?
Now, what do I mean? Okay, so I guess I really do mean bundles. I think I really do mean, wow, this is, I'm gonna just call that a typo. I really should have had the bundle here.
But you could fix it by just saying a point.
Or do the whole thing in points.
Yeah.
Thank you. In my next talk,
Before you do that, to me,
Yeah.
that what's in the box is a shocking thing. I mean, what you're doing is you're taking the Klein program that you should look at, and you're giving it as a definition. And a geometric object is something that there's some group of symmetries, whatever.
thank you, Nelson. I wasn't gonna say that because to me, the Erlangen program is a big deal, and I didn't want to make believe I know enough about it. to
But
say
usually
that.
it's said we're about groups, and you're going to groupoids.
Yes, I'm gonna go further, one step further from here.
Yeah, which is why Klein had trouble fitting differential geometry because he didn't know groupoids yet.
A tensorial geometric object is a special case of a geometric object where what we're doing is not just vector spaces, but tensor spaces. So I have a notation for the upper and lower index, the capital I and the capital J. So I call that bold I, and it's based on column. These are column notations, and I put a T there for transpose for the rows. But it's still R contravariant indices and S covariant indices. And there's a typical element of that. And the smooth maps on U is an infinite dimensional vector space, but it is over the scalars. And so if you take the exponent of that by the indices, you get the RS index smooth scalar field on a domain. But let's face it, you're just talking about a bunch of index smooth fields. Well, that's a tensor. Okay, so this is, so I'm talking about tensorial geometric objects of the geometric objects relative to the diffeomorphisms made out of tensors. And they make some interesting algebraic structures. You have this infinite dimensional scalar vector space, but you also have the scalar fields can multiply vector fields, as in a module, because you can't always divide by zero. If a scalar field has zero values, you can't do that. But at least you have a module, which is a generalization of a vector space. And all of that is built into this concept of tensorial geometric object.
Is a tangent bundle an example of a geometric object?
No, the tensor is a geometric object, not the bundle. But each tensor in the bundle is an object. That's what I'm saying.
Again, we have the issue of, are we defining this on points or on entire domains?
Well, thank you for keep reminding me about that. And I should say that wherever I say field, I'm thinking fields defined at points. So everything is ultimately defined at points. So is that enough to give a yes to your question?
Yeah. It's weird because the category that is the domain of your functor is not that. The objects in that category are like.
Well,
Sorry, can you go back to your functor that goes to the finite dimensional vector spaces? No, sorry, that's too far. Yeah, just there.
Functor.
You're sending
bundle here. I think that's what you keep correcting me.
diff, which has as objects.
The objects are open sets.
Yes. Using, yeah, right. Your functor is not defined on the entirety of that category.
No, it's a subcategory consisting of the same object, but only their diffeomorphism. I still have all of the objects.
You're only applying the function to the points. Yeah. It's not, the functor is not defined on the entire domain. That's what it is. It's only defined on the points. Which aren't even open sets.
Yeah.
All of that is true, but this category has as its objects not points. It has as its objects domains of points.
But domains are open sets.
They are.
Points are not open sets. At least.
Or I guess you could make a, maybe a category where the object is a open set and a point in that open set.
I'm not sure that there's a difference.
As a diffeomorphism that, map the point to the.
Open, that's what we need to join
to my
point.
that might work. Point open sets of open set. Then you have the vector assigned to that point.
I appreciate the clarification I would need to make to bring it home to you. And I agree that I'm not assigning a finite dimensional, well,
Well, otherwise, either you keep the open set, you have a whole field of things, or I have to pick a point and just say I have the vector at that point, right?
once you do that, you're talking about bundles, sections of bundles.
Sure.
Yeah, I'm thinking the whole time that you're speaking, a geometric object to me is basically a sheet.
Yes,
Uh,
I would like to go there,
Yeah.
But a
but
sheet,
not in this.
sheet is the sign prescribing things to.
Yeah, that's a pretty standard development.
And that's what Jippity
of,
told me
of
about.
answers.
Yeah, I agree. I agree.
That's fine, I'll just shut up.
Oh, please don't do that. Because as we see, there's some things that have to be cleaned up. But overall, I take it that you'll accept it overall.
Well, what I'm curious about is where is your presentation gonna deviate from what I already know about sheaves?
I'm not giving a lecture about sheaves. If there's an implicit sheaf theoretic underpinning that has yet to be written down. I haven't written it down. Jippity wrote something down that connects domains to manifolds using sheaves.
Right.
And I'll be happy to provide you with that write-up. I have it. It's in LaTeX, ready to go. But it's not part of the talk. I'm personally not equipped to do that in detail. I do believe that there is a problem here.
Yeah, I was wondering about that.
That's the problem.
Yeah, right.
Is that, would you agree to that? This
Yeah.
choice here?
Why is that the issue?
Oh,
Because we were saying about the whole.
I'm not gonna step on my own feet in
Get-
public.
No, I mean, is the objects to which you're applying the functor are not.
Yeah. So what is?
Okay, what is, would you like to dwell on this and
No, can we do?
put it as a question?
Let's do it later. Let's get all the slides done.
Yeah, we don't need this part of the presentation. Okay.
Oh, yeah, please.
Go back.
So, I am thinking that this is the thing we're talking about. Okay. So that is a bunch of indexed, multiply indexed smooth functions, smooth scalar functions. So I think we can build it on that. And it has a Jacobian, and so you get TRS of a diffeomorphism, and we get to covariant calculation. Covariant calculation, according to the presentation I'm giving, is a natural transformation from a product of functors, geometric objects, to another geometric object. And this goes way back to the earliest slide where the textbook showed those formulas with the A, B's, and C's. That's what this is. That's the calculation, the type of calculation generalized. And so covariance is just naturality in general. When I say in general, I mean other kinds of groupoids than just diffeomorphisms. For example, in special relativity, you have the Lorentz-Fitzgerald transformations, which are a special case, but they do form a groupoid, right? A group actually. So this is a generalization of that. So bottom line, tensors are functors and calculations, forms of calculation are natural transformations, which I'm hoping to lift these coordinate textbooks to the level of category theory. That's kind of, I'm hoping to be a worthwhile thing to do. Getting back to particular technology for general relativity, we need a notion of curvature. And a curvature is a trilinear map given by this formula. And right here is the Lie bracket. And that is why I proved the Lie bracket is covariant, is because curvature is covariant, being a sum or difference of covariant things. We know that the covariant derivative is covariant, covariant dash derivative is covariant, Lie bracket is covariant, so curvature is covariant. And
Does that mean that like naturality squares, if you put them next to each other, that they're still natural?
I should hope so. I certainly should hope so. I haven't done it.
Yeah.
But that's, and the ELF coordinate of a 3-input thing has 4 coordinates altogether. L and IJ and K. And you see that in all the relativity textbooks for curvature. And they do make a point that if you calculate the lead derivative of the basis, it's zero. Basis pairs is zero.
Naturality squares compose in two ways. Do you have a similar thing?
I don't know. It'd be good to know.
I would love to know. And I also want to ask about contravariants, but not now, after this.
I haven't seen physicists use the word contravariant.
Well, but the point is here, point is the word covariance is kind of overloaded, because there's one
Yes.
sense, which usually people use the word equivariant for instead means that it's
Yes,
transport.
thank you for,
Then there's covariant as opposed to
Yeah.
contravariant, which is something different. The word contravariant here is overloaded.
covariant.
Yeah,
Yeah, covariance is equivariant.
yeah.
So, okay, there's that, and then you can calculate on it with a little bit of algebraic strings. And then you get this nice algebraic, well, I think it's nice, algebraic string diagram for curvature. 1 contravariant, 3 covariant indices, and you don't need to mention the indices much at all. I labeled the upper one L just to keep it consistent with previous notation, but you don't need that. It's just a line. And now I'm going to get in trouble again about what the functors.
No, I know how to fix it now. It's fine. I'm not gonna say it.
So in the literature, they often talk about push forward and pull back. And the push forward has to do with a tangent vector in the domain tangent bundle going to a tangent vector in the codomain. But that does not transfer sections because the functor might not hit everything in the codomain. But if you have a diffeomorphism, you can use the pullback of the inverse to get it go both ways. So that's what this says here. And now we get to sort of the real nitty-gritty stuff of general relativity, because you need a metric. Now, metric is a symmetric positive definite tensor, twice covariant. Well, here I'm showing it twice contravariant. You can move it up and down, as I'll show in a minute. Okay, so there's the definition of it, and in high school we learn how to take scalar products, and that's what it is. Except if you want to move it to a whole manifold, you have to glue together the scalar products at each of the points. And they use a partition of unity to do that. It's a standard thing, and it's in the Abraham Morrison book. I don't need to do that because I'm not using manifolds. I'm just doing it on a domain. So it's really, the Riemannian metric is a very simple thing in this context. And so they use sharps and flats to define linear isomorphisms that are dependent upon the metric. And so here's a proof of how you get the sharps and the flats. Sharp goes from the dual tangent bundle to the tangent bundle, and the flat goes the other way, where it is. Here's the flat. The flat comes from the closure of the monoidal category. Not a very hard thing. But it's nice that, you know, category theory gives us something that's useful in this, I don't know, elevated mode.
I think the idea is flat lowers indices
Yes.
as it does.
Yeah.
Oh, you see, I didn't know that.
Flat.
Yeah.
Frequency down.
Right.
And sharp raises.
Sharp raises.
Well, the way I remember it is because the bottom corner of the flat points downward. It looks like an arrow, and the upper line of the tic-tac-toe board points up. But now, if you look up musical isomorphism in Wikipedia, you'll find that it's like 2-3 pages of discussion going every which way, and it was bizarre for me, so I boiled it down to one derivation.
Lowered the cognitive load.
Yes, sir. I don't know where this goes, so let me just see where this goes. Let me go back. Oh, yeah, it goes back to the double dual. It's all made true by the double dual in the monoidal category of dimensional vector spaces. So I think this goes back, yeah. Okay, so you have these index raising and lowering maps, and they are covariant. I'm not proving that, but they're pretty straightforward. They're linear through and through, no conditions, nothing special. But that's an important lemma because well, okay, I'll come to the because in a second. I just want to say the fundamental theorem of Riemannian geometry is that if the covariant derivative of the metric is zero, that is to say, if it doesn't change across the manifold, even though the manifold is curved, if the covariant derivative is zero, and if it happens to be symmetric in the two lower covariant indices, which they call torsion-free for a geometric reason, which I'm not qualified to explain, but that's what they say. If you flip the IJ, then it's torsion-free. That is a geometric concept. It's very beautiful, but I can't.
Well, it's a very simple way to draw with a parallelogram. We can do that after.
Yes, with the
But you've
parallelogram.
still got 7 more slides to go, so I don't wanna.
We're almost there. We're almost there. Okay, then gamma is determined. You get an affine connection for free if you have a metric tensor with these two properties. So we want to prove that. So I found in a book by the way, this is the formula for the affine connection in terms of the metric. There's the formula. It's a standard formula. All written nicely here, string diagram. Okay, how do we prove it? Well, we use the Willmore-Palatini theorem for covariant derivative of higher dimensional tensors. So we take the covariant derivative of the metric tensor three times by changing the order of the indices. We got 3 indices. There's the covariant derivative index and the 2 indices of the metric. And so what we're going to do is we're going to call them IJ and K, and we'll put them in straight order, IJ and K, and do one of them. That's this one. And since it's 0, that must be equal to 0. Then we take the K and put it at the beginning. So it's KIJ. Well, that's another calculation. So that's also 0 for the same reason. And then we put it at the right end. As you never know. So they're all 0. So we add them together. Well, if they're all 0, we add them together to 0. And you draw the string diagrams, algebraic string diagrams for those, and lo and behold, you get some cancellations. That one, the green one with the green one, and then there are 2 terms left. This term here, and this term here. By torsion free, you can flip these 2 down here to get the same as those 2 there. So you get 2 copies of this thing. You get 2 copies. So you take those 2 copies, bring them over to the other side, solve the equation. Well, I didn't solve the equation. You bring them over, you bring this over to here and put a minus here and a plus there, and then you get the original formula that they give for transformation of an affine connection. Okay. Now comes the beginning of the end of the talk, because not only are the sharps and flats covariant, but also contraction being a totally linear operation, that's also covariant. Addition of fields is covariant. Scalar field multiplication. This is a lemma or proposition of all of the ingredients that you could use by combining them using composition and tupling. Well, that's the covariance manifest covariance theorem, is that if you combine these things using just tupling and composition, the result is always covariant. That's the point of the talk. Manifest covariance, in other words, is syntactically obvious. Just look at it. So give a little language for it. A tensor calculation is one of those things where I showed F1 times Fn going to G, natural transformation. That's the form of a calculation. That's the form. It's natural. Category theory. It's natural. And so you have my favorite kind of theorem. I've always wanted to prove a theorem that is proved by structural induction. There it is. You got the lemma or proposition, all these pieces that can be combined in known ways by composition or coupling. And when you look at it, it's obviously covariant because you know the pieces are. That's the heart of the talk. Give some examples. The electromagnetic force potential, according to Wikipedia, can be given by this formula here. Never mind what it is. This is physics. I'm not going to try to explain physics. I just use formulas. But you don't like these partial derivatives here because covariance is always about the covariant derivative, not about partial derivative, which is coordinate dependent. But using the Wilmore-Palatini type theorem, you translate using these equivalences and add them together and you get a cancellation. And now this thing is covariant.
Well, or put another way,
Yeah.
differential, you could say that, the A is a one form, F is an exterior derivative, and you're just showing that the exterior derivative is covariant.
Yes, sir. For this case. Well, in general, it's
for two forms,
yeah.
and then do for n forms, you just have to anti-symmetrize.
Penrose has a fantastic notation for anti-symmetrization.
Yeah, I mean, basically the reason it works because your gamma is symmetric in the things, in exterior derivatives, like anti-symmetrized, that's why the gammas go away.
Here's one more example. Einstein's curvature tensor, written with my diagram.
Yeah.
That's essentially one more slide coming, which is to thank you. How much time did I do?
Perfect. I just before we ask, are there any questions online? Andre's clapping. Andre, good, bless you. Sorry. Any questions? Any happiness? I just think it's beautiful. Whatever. You skipped special relativity. It would have been easier.
Well, general is more general.
Right. Anyways, okay. Thank you, everybody. Next, 1 second. Let me just say a few things. Next week, we are having Joseph Helfer. Oh, welcome. And he's talking about set theoretic universes and the paradoxes of elementary two-topology. So next week, same time here. And sorry about the mess up or whatever. We're getting the Zoom working perfectly. Anyways, Giannis wrote, great talk. Anyways, ladies and gentlemen, thank you very much. And we wish you the best. Take care.
Well done.